the march of emperor penguins, steady against the icy winds of Antarctica. These conditions may seem harsh, but they remain critical to the survival of this threatened species.
If nothing happens, the emperor penguin might be quasi-extinct by the end of the century.
Climate change and the shrinking sea ice in the Antarctic signal danger for the emperor penguin.
The less sea ice you get, the more impact storms and waves have on the sea ice that emperor penguins breed on.
Now, a friendly little robot, armed with cutting-edge technology, is providing groundbreaking data that could protect the future of this species.
Every ecosystem can adapt. The question is, how fast can it adapt?
Emperor penguins, the world's largest penguin species, are a vital part of the Antarctic food chain. They prey upon krill, squid, and small fish, and in turn feed predators like larger seals and orcas. Because of this unique position, they act as a sentinel species for the global impacts of a changing climate.
Emperor penguins are an apt proxy species. If you understand how they are doing, you can understand how the ecosystem is doing.
Daniel Zitterbart studies penguin colonies with a small team around Antarctica and sub-Antarctic islands.
We're trying to understand what is the adaptive capacity of the emperor penguin. Every ecosystem can adapt. The question is, how fast can it adapt? So we employ emperor penguins, in a sense, to understand how are the changes of the physical environment projecting to the ecosystem.
To gather crucial data in one of the world's most extreme environments, the team needs to be innovative, because these flightless birds breed and molt in colonies on land-fast sea ice.
Land-fast sea ice is frozen ocean that's also frozen to a piece of glacier that's stuck to land. So land-fast sea ice is a very, very stable platform and can be stable over months, sometimes even over years.
And this brought the team to a colony in Atka Bay, an expanse of sea ice about 10 miles long and wide. Each year, 300 chicks are equipped with a radio frequency identification, or RFID chip, like the ones used in dogs and cats.
We have to do this with RFID chips because emperor penguins are undistinguishable visually.
These chips will allow Dan to track returning chicks through adulthood. But because the chip does not have its own power supply, it can only be scanned from a short distance.
Now, imagine you have 20,000 penguins at a time and spread out over an area of several square kilometers or square miles, and you need to scan each individual penguin, so you need to approach them up to 3 feet. How do you do that? Usually, with most species, you build a fence and you make them go through a gate. And we do this with different penguin species. It's impossible with emperor penguins because they live on the sea ice. So we needed an antenna, and we needed a mobile antenna, and we needed a smart mobile antenna that can move itself to the penguin. And this is how Echo was born.
Standing at 2 feet tall, Echo is a fully autonomous rover integrated with AI technology designed to track the Atka Bay colony. Zitterbart and his team are testing their new penguin guardian this year for the first time in Antarctica.
Echo is an autonomous robot on wheels that can approach penguins, scan them, and then go to the next penguin. It can do this without getting bored, without getting tired, very, very slowly and very silent. And those are critical things for minimizing our impact. We don't want to scare the penguins. It's very important to us that Echo itself has no impact on the penguins.
The robot uses a mobile radio antenna in conjunction with a penguin observatory to listen for an echo from the radio tags.
Echo has 4 main sensors on it. It has a 360-degree camera, which we use an AI on that imagery to detect the penguins. Once a penguin is detected, it turns on a 3D camera, which can measure the distance to the penguin. And to understand the scenery, Echo also has a LiDAR. A LiDAR is like a laser that spins very fast and gives you a 3D distance picture of the world to make sure it doesn't run into any obstacles. So the robot can approach up to the distance we know we need to be. Once it's close enough, the robot turns on the antenna and tries to scan, tries to see if it gets a response from this individual penguin. We don't know if that penguin is chipped or not.
Echo will track the chipped individuals year-round over the coming decades, recording which penguins survive, how long they live, and their breeding success.
Last year we got lucky and scanned the first few that came back and now are adults and now are contributing to the breeding colony.
And understanding population dynamics is only the beginning. Echo is part of the MARE program. Monitor the health of Antarctic marine ecosystems using emperor penguins as sentinels.
You can use the emperor penguin as an alarm bell, like as a canary in a coal mine, to see what happened at all the colonies around Antarctica this specific year. Echo is part of understanding the adaptability and long-term consequences and ecosystem health. We have the part of understanding the habitat at sea, where we put loggers on the penguins, they go, swim, come back. And we have the remote sensing part, where we try to use the knowledge we can gather locally to understand emperor penguins on a global scale. We are gathering a lot of knowledge on how to make a robot interact with animals that interact in real time.
The tests this year are helping to get Echo penguin ready.
The challenging part is to teach it to behave properly. As a human, we have an instinct on how to behave properly. We learn very fast when you work with an animal what's good and what's not good. The robot does not. So we need to teach the robot how to be smart about it. And that's a very challenging process.
Emperor penguins are incredibly curious creatures, allowing Echo to integrate into the colony, except when it's a little too noisy.
The robot needs to be aware of the environmental conditions, ideally even of its own sound. We had instances where, for example, it was so cold that the rubber of the wheels made squeaky noises on the ice. Really bad. Penguins didn't like it. While if it's quite windy, they don't care about anything because they don't hear it. So one of the very important things is for the robot to understand when can I actually work.
Luckily, Echo's got some extra eyes and ears on the ground to help. A single penguin observation and tracking observatory named Spot.
We have a container there with like 20 cameras on top, and they always have the entire view of where's the colony, how is it standing, how is it behaving.
Spot gives the team the context needed to advise Echo on where to drive and when to move, minimizing disturbance to the colony.
The penguins are behaving much better than I thought. They are minding the robot only in very few circumstances, and usually they don't mind it. So to me, the breakthrough is that we actually managed to get it working, to get emperor penguins and autonomous robots working together.
Once Echo is accepted by the colony, researchers need to find ways to conserve precious battery life out on the ice.
Emperor penguins come all together when it's really cold and huddle. And as for the penguins, as for the robot, energy is scarce. So we want to drive around as little as possible. And we know when emperor penguins are in a huddle, they move downwind. So one of our plans to operate Echo in winter is actually to place it downwind of an emperor penguin huddle and then let the huddle move itself around the robot and past it. So we don't have to drive the robot. We have basically no impact on the penguins because we park far away. So we can predict their motion, place the robot smartly. Once they are around the robot starts to scan, they pass on. Once they are in a safe distance, the robot starts to move, comes back, and it can do this over and over and over until the battery is empty.
In addition to smart placement, the team hopes to have solar garages that can recharge Echo and shelter it from passing storms to extend its autonomous time in the field.
I think it's one of the first experiments where we actually have a robot autonomously interacting with such a large group of animals. And that is the challenging but also the interesting part.
Although this research will take decades to provide answers on adaptability, scientists are observing new behaviors every season through the MARE program.
We learned over the last couple of years that emperor penguins use vision for navigating on the sea ice. So in days of good weather, they just walk straight to the colony and they don't take very little detours. While if the weather is very snowy and you don't see very far and you can't make out the icebergs, they don't know how to navigate directly to the colony, so they just follow the wind until they hit the ice wall of the glacier, of the shelf ice, and then follow the ice shelf down until they hit the colony. What we learn is they always take a fixed detour, a fixed cost, compared to wandering around and searching for the colony. So they don't have to search, they accept the fixed detour way.
The team is even using new findings to inform better protection measures.
Another thing we learned is that juvenile emperor penguins swim way further out than adults, because juveniles can spend years in the water until they come back to breed.
This discovery shines a light on the vulnerabilities of the younger penguins.
Right now, all the protection measures, like marine protected areas, they focus on the breeding colony. They don't focus on the juveniles. But if we don't take care of the juveniles, we won't have young adults to recruit back into the colony.
Emperor penguins produce 1 egg per pair each year, and with only 10% of those eggs making it to adulthood. Protecting juveniles is vital for this threatened species.
We tag juvenile emperor penguin chicks with those satellite tags every second year. Knowing where do the juveniles go and planning our marine protected areas to also protect juvenile emperor penguins, not only adults, is critical.
In parts of the Antarctic Peninsula, sea ice cover has already reduced by over 60% in only 30 years.
We have the lowest Antarctic sea ice extent ever measured. It's beyond 6 sigma of what it used to be. That means it's the chances of it being randomly like this and not impacted by climate change are less than 1 million. So the Antarctic is already changing.
As the ice diminishes, threats to the breeding colonies increase.
The less sea ice you get, the more impact storms and waves have on the sea ice that emperor penguins breed on, the one that's very close to shore. And so if this breaks up, then the whole generation of emperor penguin chicks might die out with one instance. And so that can have very severe consequences on the emperor penguin within just a few generations.
Scientists project that 99% of the world's emperor penguins will disappear by the year 2100 without major cuts in carbon pollution.
We lost 2 generations in 2016 and 17 at a colony next to Halley Bay because the sea ice broke up too early. So that already happened.
While ECHO works to safeguard the future of emperor penguins, other monitoring programs across the globe are looking to this model for inspiration.
This is transferable not only to penguins, this is transferable to other species. You know, when you think about sheep and you're herding sheep with a robot, or when you're thinking you want to scan cows. What we learn in Antarctica, because it's so pressing to learn it there, can actually help other researchers in the future not to have to start from zero.